welcome to Oddly Real. I'm Nem Stefanovic. Physical objects in our universe possess an inherent property called mass. Mass is responsible for certain aspects of motion, like an object at rest wanting to stay at rest, or an object in motion wanting to retain that motion unless acted on by a force. It's also a component of momentum, which determines the amount of punch that an object delivers on impact with another object. A simplified way to think about mass is that it's the amount of stuff that's present in a body. However, this isn't the whole story. For example, two objects like wads of putty can collide with equal and opposite momentums to stick together as one large wad at rest. Yet, in this situation, the resultant mass of the large wad is actually more than the sum of the masses of the two smaller wads. Additionally, take a system of masses which we define as a group of separated masses that are independent of each other and may or may not interact. This system can have a mass that is larger than the sum of the individual masses. Perhaps stranger still, electromagnetic radiation like light is made of massless particles called photons. However, if there's a group of such photons together, they too can possess mass. It turns out that mass is not simply an additive property. The sum of the masses of a system of particles in general is not equal to the mass of the system. In order to understand mass, we'll explore the relationship between mass, energy, and momentum in spacetime. For example, consider the collision between two similar, rigid metallic balls that are suspended adjacent to each other. If one of the balls is pulled back, we'd be adding energy to it in the form of potential energy. We know the energy is there since if we let go of the ball spontaneously starts to fall and speeds up as it moves towards the second ball. The ball converts its potential energy into kinetic energy of motion, speeding up. Right before the ball collides with the second ball, the moving ball has converted all of its potential energy into kinetic energy, and it is moving at its fastest speed. By the conservation of energy, the total kinetic energy before the collision must equal the total kinetic energy after the collision. In this case, upon colliding, the first ball will continue to a complete stop, and all of the ball's momentum will be delivered to the second ball. This means that the second ball will now continue at the same velocity the first ball had before the collision. The second ball will now start moving up, converting its kinetic energy into potential energy and slowing down. Eventually, the second ball will fall back down, and the same process will repeat in reverse and continue over and over again. The two balls exchange their roles upon collision. Notice that the total momentum and the total energy are the same before the collision and after the collision. There's a very deep relationship between mass, energy, and momentum in spacetime. We live in a four-dimensional spacetime that consists of 3 dimensions of space and 1 dimension of time. When measurements are made in spacetime, like lengths or time intervals that are measured, the result will depend on the reference frame of the observer. Someone traveling close to the speed of light in a rocket ship will get very different measurements compared to someone at rest on Earth who is measuring the same thing. However, there is a 4-dimensional entity called momentum energy, or Momenergy, that exists independently of any reference frame observer. Momenergy is the representation of a mass that is moving in a direction through 4-dimensional spacetime. It has 3 components directed through space and 1 component directed through time. The spatial components capture the momentum of the moving object. The time component appears as the energy of the body. The magnitude of Momenergy is exactly equal to the mass of the moving body. Momenergy has a reality all its own, making it more real than what we can observe by measuring energy and momentum separately as observers in one frame of reference. There is an explicit relationship that links mass, momentum, and energy together as components of Momenergy. This relationship is the mass squared is equal to the energy squared minus the momentum squared. Notice that mass is constant, so if the momentum of an object goes up, that means the energy of the object must also go up to ensure that we get the same value for mass. If momentum goes down, that means the energy of the particle must also go down. Next, let's consider an inelastic collision where the two colliding masses are made of a substance like putty. Let's say that both balls of putty are similar and released at the same time with equal but opposite momentums. Right before the collision, the momentums are of equal magnitude but opposite directions, so the total momentum of the system is zero. After the collision, the putty sticks together in one body with the same total momentum, which is zero, meaning the amalgamated putty is at rest. Before the collision, the total system energy for each ball of putty, including its mass energy, is the mass plus kinetic energy of motion. So the total system energy is 2 times the mass plus 2 times the kinetic energy. After the collision, the energy must be preserved, meaning it has to be the same as that before the collision. However, after the collision, there is no momentum and the putty is at rest. So all of the energy in the system has to be in the form of mass, meaning the mass of the single ball of putty after the collision is 2 times m plus 2 times the kinetic energy, which is greater than the masses of the individual balls of putty before the collision. How can the putty have more mass, and what's the source of the extra mass? Here, the extra kinetic energy before the collision is converted into both plastic deformation and heat. Both types of energy contribute to the mass of the larger ball of putty at rest. It might be surprising that a system of objects or particles can have more mass than the mass that's contained in the individual objects and particles that make up the system. So where is this mass if it's not in the sum of the individual bodies within the system? Consider one particle within a system of particles like an atom. The extra mass isn't within the atom, and the particle doesn't acquire mass from its motion, so it's not there. It turns out that the additional mass in the system isn't due to the individual parts, but the system as a whole. Heat is a result of relative motions between two or more particles, not individual particles on their own. This makes heat a system property. Similarly, the mass of a system of particles is greater when the particles move relative to each other. Furthermore, if two objects slow down and come to a stop as part of a collision, that means that there is some force involved, whether gravitational, electromagnetic, or nuclear. If forces act on particles, then it means that the particle force field is storing energy. This energy has to be accounted for, and it leads to a mass that is greater than the sum of the objects in the system. Consider an example where there are only two massive bodies in a system. Both have the same mass and both are moving toward each other with equal and opposite velocities. Each object has a mass of 8 units. The energy of each object is the square root of their masses squared plus their momentum squared, which is equal to 10. The total energy of the system is 10 plus 10, which equals 20. The total momentum of the system is 0 since the momentums of each individual object are equal and opposite. Thus, if we calculate the mass of the system of objects, we get a mass equal to the square root of the system energy squared minus the system momentum squared, which gives a value of 20. Thus, the mass of the system of the two objects is 20, but the sum of each mass of the individual objects is 16. There is more mass in the system of objects than in each individual object. Once again, it needs to be emphasized that mass is a system property, and it's not simply additive. What's extraordinary here is that the two masses don't even have to interact with each other. They don't need to collide, and there doesn't need to be a link between them in any way. Yet, when considered as a group together, The system as a whole possesses energy, momentum, and mass as if it was a single object. Moreover, the nature of spacetime itself demands that there is a conservation of total momenergy in an isolated system. The system momenergy does not change regardless of if the individual components within collide or not. Both the direction and momenergy in four-dimensional spacetime are preserved. Since the length of the momenergy vector is the mass of the system, that means that the system mass will remain the same. More specifically, the mass of the system will also be completely unaffected by the decays and annihilations of its constituent parts. Some particles, like photons of light, exist as pure energy without mass. Photons behave like other particles in that they can collide with other particles like electrons. If we look at our equation for momenergy and we set the mass equal to 0, we see that photons will still carry energy in the form of momentum. This means the particles can deliver an impact against other particles in a collision. They travel through spacetime at the speed of light and do not age with time. If we were to draw the momenergy vector of the photon through spacetime, it would have a tip and tail, but its magnitude would be 0, representing the 0 mass. For example, a photon can collide with an electron that is at rest. Let's give the photon an energy of 1.0022 mega electron volts, which is twice the energy of the electron mass, or 0.511 mega electron volts. And we represent the photon velocity, v, equal to 1, meaning it is traveling at 1 times the speed of light. After the collision, the electron is kicked forward at a speed of 92% of the speed of light, while the photon is scattered backwards with less energy and momentum. The total momenergy of the system before and after the collision is the same. Thus, photons can contribute energy and momentum to a system. Let's look at another example involving a system that contains a photon and a body with mass m that is at rest. In this case, the photon has 3 times the energy of the mass, m, of the body. This means that the system has a total energy equal to the sum of the energies, or 4m. Since the body is at rest, the total momentum of the system is defined by the momentum of the photon, which is 3m. We can then calculate the mass of the system as equal to the square root of the square of the system energy minus the square of the system momentum, which results in a value of 2.646 m. Even though the system only contains one body with mass, the presence of the photon in the system yields a total system mass equal to over 2.5 times that of the body mass. Perhaps an even stranger example is a system consisting of 2 photons. Each particle has 0 mass. One photon has an energy E, and the other photon has an energy 3e. The total system energy is 4e. The particles are moving in opposite directions of each other, so the total momentum of the system is 3e minus e, or 2e to the right. We can use these values to calculate the system mass as the square root of the system energy squared minus the system momentum squared, yielding a value of 3.464 e of mass. A system consisting of massless particles actually has mass. I hope you found this episode interesting, and remember, oddly real, really interesting.